Today we're going to do applications of finding maxes and mins, which typically we call optimization. I'm going to do 3 problems with you. The first one involves distance. Here's the distance formula, and typically when we want to maximize or minimize distance, we max or min the distance squared. And the reason for that is when we use calculus to find critical numbers, we don't have to worry about the square root sign. So let's just jump into this first problem involving Mr. Toad. The problem's over here. Mr. Toad is on the parabola y equals x squared, and his home is over here at 0, 1. And we want to know at what point on the parabola is he going to be closest to home. So we want to minimize the length of this yellow line. And I've got a Desmos file here I can show you. Here's Mr. Toad moving along the parabola. That red dotted line you're seeing is his distance from home. So it's the length of that black line between Mr. Toad and home. And so we can see when Mr. Toad is at the bottom of the parabola, he's farthest from home, well, locally farthest from home. And then he seems to get closest to home. I'm looking at the y values on this red dotted line. He's closest to home here and again over here. And then he just gets farther and farther and farther from home. So let's see if we can use calculus to find those 2 points. So I'm going to let f of xy be the distance squared between Mr. Toad and home. So in my distance formula, the 0, 1 down here is my x naught, y naught, and then the location of Mr. Toad is xy. So f of xy is x minus x naught, which is 0, squared, plus y minus y naught, which is 1. Squared. Now that's a function of x and y, and to use our calculus methods, we need a function just of x. So here's the part where we use the fact that Mr. Toad is living on the parabola. Y is x squared. And so we can replace y in that formula with x squared. And so we get x squared plus x squared minus 1 quantity squared. And we want to minimize that function. So now we're going to find the critical numbers and classify. So I need f prime. Now I could multiply f out first and then take the derivative, but instead I'm going to leave f like it is and use the chain rule. So 2x plus, for the next term, we bring the 2 down, we leave the inside fixed, and then we multiply by the derivative of the inside. Okay, and let's clean that up now. That's 2x plus 4x cubed minus 4x. And we can go a little further. That's 4x cubed minus 2x. All right, so I want to set f prime of x equal to 0 to look for the critical numbers, because there are no places where f prime doesn't exist. That's the other place you might see a critical number. So we have 0 equals, I'm going to factor the 2x out, 2x squared minus 1. So our critical numbers will be when 2x is 0 and when 2x squared minus 1 is 0. And the second equation means x squared is a half. So the first equation, 2x equals 0, gives me x is 0. And the second equation gives me 2 critical numbers, x equals plus or minus the square root of 1/2, which we can simplify as 0 and plus or minus 1 over root 2. So I've got 3 critical numbers, and I want to plot those on an f prime number line and look for local maxes, local mins using the first derivative test. And I went ahead to save time and I did that, and you should verify my number line. And it looks like if my number line is correct, I've got a local min here, a local max at 0, which we saw on the computer, and then another local min here at 1 over root 2. So our conclusion is that we've got 2 local mins. One at negative 1 over root 2, one at positive 1 over root 2. And the question is, what's the y value? Remember, we're looking for actual points on the curve. Question is, at what point on the parabola? So we need to use this, the fact that y is x squared. That gives us the y value for each x down here in our critical numbers. So this will be negative 1 over root 2 quantity squared and 1 over root 2 quantity squared. So if we clean that up, we get 2 places where Mr. Toad is closest to home. Negative 1 over root 2, a half, and positive 1 over root 2, a half. So that would be about here and here. He's closest to home. Okay, let's do another one. And again, we're going to take some time to interpret what the problem is asking for. Albus and Agnes live in a rectangular pen that's inscribed in this triangle that you see here. And we want to know 2 things. what dimensions will maximize the area of their pen and what is the maximum area of their pen. So I've got another Desmos to show you. Here's Albus and Agnes, and their pen is inscribed on that blue triangle. So this corner here of the pen has to stay on that blue line. And the red dotted line that you see is the actual area of their pen. So you can see the area of their pen gets very small when it's narrow, and again, very small when it's long and flat. And it looks like the max area is there when the length is 3. The x coordinate is 3. So let's see if we can verify that. All right, our setup. Area of xy. So this is going to be the area of their pen. Now the area of a rectangle of length x and height y is xy. All right, again, we need to write that as a function just of x. And we can use the fact that we know what y is. Y is 3 minus 1/2 x. So that's 3x minus 1/2 x squared. And the domain of our area function is 0 to 6 because those are the boundaries on the x-axis of the triangle. All right, so now we're going to find critical numbers. So we're going to take a prime of x and set it equal to 0. So a prime is 3 minus x. So a prime of x is 0 at x equals 3. And that's what we just saw. So that's our one critical number. Now, we've got two options. We could make a first derivative number line like we did in the last problem, or just to shake it up, I'm going to use the fact that I have a continuous function on a closed interval, and I'm going to use the method that we did in section 4.3 for finding absolute max, absolute min on a closed interval. And again, to save time, I went ahead and evaluated the area function at the two endpoints, 0 and 6, and at the critical number, 3. Now, we get 0 area on the boundary points, 0 and 6, so those aren't giving us our max area, but we see that the area is a maximum when x is 3, and the area function gives us 9/2. So here's our conclusion. The max area is 9/2. Whatever units, let's say meters squared. And the dimensions, because we were also asked for the dimensions, are x equal 3 and y equal, so we need to interpret what the height is when x is 3. So we're going to plug 3 into this equation here. Y equals 3 minus 1/2 x. So that would give us y equal 3 minus 3/2, which is 3/2. So these are the dimensions of the pen, 3 by 3/2. Okay, and that's that one. So I'm just going to do one more with you, and then you have another one to read on your own that's very similar to a homework problem. Okay, so we want to construct an open top box with square base that has volume 500 feet cubed. Now, if the base is square, that means if this dimension is x, then this dimension is x, and the height is y. We want to know, again, two things. What dimensions will minimize the surface area, and what is the minimum surface area? So step one, we need a formula for surface area. So S of x, y. The surface area will be the surface area of the base, which is x squared, plus the surface area of the 4 sides. Each side has surface area x times y, so we'll have 4xy, and that will be our total surface area. Now again, we want to write that as a function just of x. And the way we're going to do that is we're going to use the fact that the volume is 500. Now the volume of that box is the area of the base, x squared, times the height. So let's solve that equation, this equation here, for y. Y is 500 over x squared. And we'll come back to that later when we get the dimensions of the box. We'll need that formula for the height. So over here in my surface area, I've got x squared plus 4x times 500 over x squared, which is x squared plus 2,000 over x. And our domain here is simply x greater than 0. Okay, now we're going to find critical numbers. We want to take s prime of x, which is 2x. And then for the next term, 2,000 over x, we want to think of that, here's my scrap paper up here, as 2,000 x to the negative 1. So when we take the derivative, we'll have negative 2,000 x to the negative 2, which is 2,000 over x squared. So pause, make sure you follow that. All right, let's write that as a single fraction without negative exponents. So the common denominator is x squared, so I'll take 2x and multiply by x squared over x squared. Subtract 2,000 over x squared. And that gives me 2x cubed minus 2,000 over x squared. And just go a little further, factor a 2 out, x cubed minus 1,000 over x squared. So for our critical numbers, s prime of x is 0 when the numerator is 0. And that would be when x cubed is 1,000, which would be x equal 10. So that's one critical number. And then s prime of x does not exist when the denominator is 0, and then that's when x is 0. That's not a critical number because it's not in the domain. We can't have a box with no base. So we've got one critical number, and there are two options to verify that the surface area is min there. One is to make an f prime number line, and here's s prime, which is 2 times x cubed minus 1,000 over x squared. And I went ahead and did that, and that verifies we get a local min at x equal 10. Or you could use the second derivative test, which you watched videos on. And again, it just verifies that you get a local min at x equals 10. So our conclusion here is that the minimum surface area is s of 10. Now, for s of 10, I'm using this formula right here for surface area. So I'm putting 10 in for x to get 300, and the units would be feet squared for area. So this would be feet squared. And the dimensions are 10 by, and remember, I said we'd need y later to get the height of the box. I put 10 in to this equation to get y, and I get a height of 5 feet. Okay, and that's the end of this section.